For those of you that don't know me, I'm Steve Dick, K1RF. Some of you might have seen me before here. I gave a presentation on end-fed half-wave antennas on January of 2024, and I try to be pretty in-depth over there, and I'm trying to do the same here. A little bit about me. I'm a retired electrical engineer. I was a functional group manager that developed very high-speed, high-density FPGAs and PC boards, and I've done project management, really high risk, state of the art, multi-million dollar programs with multi-disciplines, etc. And I was real busy during my working days. When I retired, I had plenty of time on my hands, and I always was interested in getting a lot of bang for the buck. So I gravitated towards wire antennas and 100-watt rig. That's it, no high power. And I learned a lot about them, and I'm trying to transfer my knowledge to other people. So that's why I'm here. Um, as you all know, Ham's always complaining about not getting out. This antenna is better than that antenna, et cetera, et cetera, et cetera. And interestingly, people are always focused on low VSWR, the multi-band wire antenna. It has to have low VSWR. But LB Seebeck, who's SK, used to say over the years he discovered that many multi-band antenna users remain unaware of the antenna patterns. All they care about is VSWR. They think they're radiating broadside to the antennas, and they could be at right angles or at 45 degrees or who knows what. So that's just as important. In search of the Holy Grail, everybody wants a multi-band, simple wire antenna that's low cost, easy to build, doesn't need a wide range antenna tuner. Like nowadays, you could get a 3-to-1 antenna tuner built into most rigs and easy to deploy. The off-center fed dipole is a good attempt at finding the Holy Grail. If you want a lot more information, you can join the groups.io OCFD group. And before I begin my presentation, just another couple of comments. I just want to give a shout out to Rick Westerman, DJ0IP. He did a lot of work with OCFDs, and he developed one for his antenna design company named Ariel 51. And his antennas are sold by Spiderbeam and by Vibroplex in the US. Another resource was Steve Hunt, who's also SK, sadly, G3TXQ. He did a lot of description on his website, carinia.net, on all kinds of antenna topics and balance. He analyzed balance very carefully. And Dan McGuire, AC6LA. Some of you might have heard his name. He developed an automated tool for EasyNet called Auto Easy. It lets you optimize antennas. So those plus a whole bunch of antenna compendium articles and other places, I've accumulated a lot of information. I also do my own simulations on these antennas. I use EasyNet and I use SimNet, which used to be called SimSmith, to show what the antenna looks like in simulations, as well as build them and try them and make sure the real antenna sort of agrees with the simulations for the most part. The Wyndham itself, which is another name for the end-fed half-wave antenna, has a storied history. Gory details could be found at this web address that I listed, but the actual antenna birth came before 1929. Somebody proposed using feeding a half wavelength wire off center with a single feed line. In 1929, this gentleman, whose last name was Byrne, wrote a thesis paper. I think he went to Ohio State University, but Wyndham, who was a lawyer, got the credit. I think Byrne was an engineer and Wyndham was a lawyer. So guess who won? But he published an article in September 1929 of QST magazine with a single wire feeder. That was later replaced over the next 30 years or so with ladder line. Then ladder line was replaced with a coax and some ugly Ballon feed. Then it went to a coax plus transformer in Ballon. 1980s, the Carolina Windham was very popular. That's a horizontal wire with a short vertical section that was supposed to give you better DX performance, which was questionable because most of the radiation came from the horizontal section and the vertical section didn't do much. It's still being sold today, but I think it lost some of its popularity. From 1980s through today, a lot of advances in both testing and simulation tools resulted in new feed point splits, better performing balance, and even an end-connected or center-fed dipole. Most designs have different feed arrangements, and they're not strictly Wyndhams, though the name is stuck and forms a kind of brand name like G5RV. Okay, this first technical slide, that very busy looking slide on the left, let me try to explain that. Gentleman by the name of Serge Struband, ON4AA, worked with OCFDs, and he made a chart up which showed that if you assume a 200 ohm impedance, by the way, 200 ohms is very nice to match because you could use a Ruthroff transformer, which is very easy to make and very efficient. Well, he said if you assume 200 ohms and you plot VSWR on each band, you'll see dips in, low points, etc. And if you could find a feed point where all of these things intersect at as low a VSWR as possible, then that should work nicely as a north center fed dipole. And his idea basically has worked successfully. This next slide is very important, and it shows a summary which was put together by Rick Westerman a while ago. He says the sweet spots have been known for almost 8 years now. It depends on which bands you want to use it on. And he showed different feed points and what bands give low VSWR. And he tried to show, okay, if it's green, it's less than 2 to 1. If it's yellow, less than 3 to 1, etc., all the way up to greater than 7 to 1 in dark orange. And he put this together over many years, and it's still a very valid chart. And here's what he says, and here's what he recommends. He says use either a 20% feed point or one of the 29% feed points. I have personally built about 20 of the ones that use the 29.7, hung them in many different locations with various lengths, various angles of the inverted V or flat tops, etc. And they always work on these 5 classic ham bands. Most of the time, I don't even need an antenna matchbox. He's not talking about 80 meters. 80 meters is very large band and it's pretty narrow band, so you're going to need an antenna matchbox or move the resonant point around to your favorite area within 80 without a matchbox. This next chart shows a recommended configuration using Rick Westerman's 29.7% feed point configuration. This antenna is about 235 feet long. Now there's a capacitor in the middle of it with a bleeder resistor. I'll talk about that later. But if you just had 2 pieces of wire with a 29.7% feed point, a half wavelength it will be 3.44 megahertz. It's too low. But you need it to be at that low frequency in order for low VSWRs on the upper bands. And why is that? Because of a thing called end effect. The ARRL always talks about end effect, but they never explain what it is. So I'll try to give you a little idea of what it is. A half-wave dipole antenna has high current, low voltage at the middle, and low voltage, high current, I'm sorry, low current, high voltage at the ends. That high voltage, if you think of this antenna as a whole bunch of little segments, the segment at the ends couples into the ground much more. You get much higher current to ground from the ends than current, say, in the middle, because current is capacitance times change in voltage over change in time. So the change in voltage over change in time will be much bigger when you have a high voltage swing on the ends. So as a result, the antenna resonates at a lower frequency than you would expect. That could be fixed by adding this capacitor right in the middle at a high current, low voltage point. And by adjusting the value of that capacitor, you could move the resonant point on 80 meters wherever you want. No capacitor, it'd be at 3.45, it's too low. But then you could go from 500 picofarads up to 100 picofarads and move the resonance around. So if you like CW, you'd use 500 picofarads. If you like sideband, you'd use maybe 300. And the capacitor has almost no effect on the higher bands. It just has its main effect on 80 meters. Now, coupling to that is what's called a hybrid balun, and I'll get into some detail on that. The hybrid balun does two functions. It matches the 200 ohms to 50 ohms, and it provides choking impedance inside the transformer. And I will be talking about that. This next slide shows some effects of feed points. For years and years, people used a 3-to-1 feed point because 3-to-1 is easy to remember. The problem with the 3-to-1, which is shown on the right side here, is that it doesn't cover 15 meters. The antenna just is not designed for 15-meter operation. Can you guys all hear me okay? Yes? Okay. Just want to make
Yes.
sure. Thank you. Just want to make sure. If you can operate, and some people do, by using a wide range antenna tuner, and they say this antenna tuner could match a wet noodle. That's true, but the problem with that is the VSWR on here with 15-meter operation is like 17 to 1. And if you're feeding it with coax, the coax is absorbing a lot of that high VSWR, and you end up with maybe 6 to 1 or something like that. And you say 6 to 1 isn't too bad, but you're dissipating most of your power in the coax. It's less than 18% efficient, and even worse, it's a high impedance on 15 meters. So you're going to develop really, really high voltages at the balun, and you have a good chance of destroying the balun. So you could do it, but it's not a good idea with the 3-to-1 feed point. I think Buckmaster sells a good quality uh, OCFD with a 3-to-1 feed point and a 6-to-1 balun. Excuse me. This other chart shows a simulation of the end-fed half wave with a 29.7% split. And if you look over here, the SWR is nice and low on 15 meters. Also, the antenna as a whole is very efficient. If you look on this left side, that's dB loss of the whole system, including the coax and the transformers and everything. You're at about a little over a dB loss, which is quite good. If you're a dB loss or less, including the coax, including transformers, you're doing really well. So it's a fairly efficient transformer, uh, uh, antenna. The OCFD, the transformer, and the feed line is around a dB of loss. Here's a 40-meter example. This one's only 68 feet long with a 40.5% feed point. This one doesn't need any capacitors because you don't have that big wide 80-meter band to worry about. And it also has pretty decent VSWRs on 40, 20, 15, and 10. And I just plotted these in the simulation. And you're well within the 3-to-1 matching capability of most modern day rigs. Now, I just want to mention one thing about simulations. Um, they really advanced. They really advanced, um, especially for off-center fed dipoles. Just to give an example, there's something called SimNAC, which was written by AE6TY. It's extremely powerful, but it has a large learning curve, but it's free, totally free. And there is a sample file provided with the tool, and the tool was called a center-loaded OCFD optimizer block by Dan McGuire, AC6LA. He's the guy who developed the EasyNet Auto Easy program, which does optimization of antennas. He moved that over to SimNet. So all you have to do if you want to develop your perfect, ideal off-center fed dipole, you start off with default values, which are basically 80 through 10 meters, let's say. You select the desired bands you want to optimize it on, set your antenna height, wire size, start with approximate wire length that you think you need, push the tune for minimum SWR, and voila, an antenna pops out, which tells you exactly how long it should be, where the feed point split should be, how far away a capacitor or inductor should be, and it gives you the whole kit and caboodle instantaneously without doing any work. This next chart shows an output from SimNet, and I'm not expecting you to understand what's here, but here's what you could do with it. You can display a graphic which has little lines on it, and these little lines show the entire band of operation. So you can say, oh, the VSWR is going from 2.0 to 1.8 on the 15-meter band. So it shows you that as well as system losses. So it's a really nice thing to visualize. And this simulation had in it a simple version of a transformer. And you could put in whatever coax you want, and it will figure all that out for you and give you an answer. So it's like amazing compared to what was available just a few years ago. Okay, on balance, now I'm going to start getting into balance a bit. The recommended balance is known as a hybrid balance. It consists of a 4-to-1 Rutherford voltage balance cascaded with a 1-to-1 Guanella current balance. The current balance minimizes common mode current on the feed line. The voltage balance is for matching, 50 ohms to 200 ohms. And different vendors don't always use 4-to-1. Some use 6-to-1. 4-to-1 is much easier to implement, and most vendors are using 4-to-1. Plus, I verified in my own simulations that 4-to-1 usually gives much better performance than with the 6-to-1. The reason you need the Guanella current balance or choke balance is that the antenna is unbalanced, and the more the feed line is off to one side, the worse it's unbalanced, and that causes common mode currents on the outside of the coax that's feeding it. And the worse that current becomes, it starts radiating and it skews the antenna patterns. It changes the SWR curves all over the place. It changes the resonance points. And worse yet, all these characteristics change with the length of coax. If you have a good choke balance, you could change the length of coax and it will have no effect. Now, a couple of things about these two parts of the compound balance. The 4-to-1 Rufa has no common mode choking. It's fine for impedance matching, but don't depend on it for any choking. Carolina Windhams use that because you don't want choking where the 4-to-1 hits the antenna. You want that little vertical piece to radiate. So that's fine for a Carolina Windham. Then there's a two-core Guanella balance, and that can do a combination of choking as well as impedance matching. And that's used by some vendors. The best one, though, is a hybrid balance. because it's the same number of toroids or toroid stacks than the two-core 4-to-1 guanella balun, but it has twice the choking impedance. So it gives you the best choking impedance with the same number of cores. And here's a key point when comparing all center-fed dipoles to end-fed half-waves. The transformers in here, the Ruth-Ruff balun, the 4-to-1, and the guanella choke balun are all transmission line antennas. Okay? Because they're transmission line antennas, they absorb any leakage inductances in the transformers like you have in end-fed half-wave antennas, and they have much higher efficiencies. You can typically get from 97 to 99% efficiencies in these transformers. An end-fed half-wave transformer, which is a non-transmission line and wide turns ratio, they're doing well at 90% efficiency across the bands. It's even hard to achieve 90%. The ARRL antenna kit for the end-fed half-wave is maybe 85% efficient in the middle, which isn't great. And why is that important? Well, who cares about efficiencies? Doesn't really matter. The other guy at the other end will hear you. Well, the thing is, on receive, you're not going to notice anything. On transmit, if you're trying to run any appreciable amount of power, depending on the toroid sizes, etc., let's compare them. Let's say you have 97% efficiency with a 100-watt rig. That means you'll have 3 watts dissipated in the core. If you have a 100-watt rig with 90% efficiency, you'll have 10 watts dissipated in the core. That means there's more than a 3-to-1 difference in how much power the core is heating up based on what looks on the surface like a relatively small difference in efficiencies. So the high efficiency lets you use smaller parts for the same power rating, as well as lower cost parts for the same power rating. That's a big deal, especially with high power. Okay, here's a picture of the Ruth-Ruff balun. This one was with a single toroid. It's using a wire transmission line that could be parallel like it's shown or a twisted pair. And that's typically about 100 ohms impedance, which you want. And typically they use type 61 ferrite material, which is very, very efficient. It's good for 4-to-1 impedance matching over wide bandwidth. Not good by itself because it's not doing any choking. And if you look at the analysis that was done by G3TXQ, if this transformer worked ideally, the current in one side cancels out the current in the other side. They're going in opposite directions, which means it has essentially zero inductance or zero choking impedance. If you get any choking impedance at all, it's because it's imperfectly built. So the Ruth-Ruff is good for voltage and impedance transformation, but it has no effective choking capability. Next one is a dual core 4-to-1 guanella current balance. The way these are interconnected, it gives you a combination of 4-to-1 impedance match and a good degree of choking impedance. So that is used by some vendors. The current balun looks like this. It's basically just coax cable wound around typically a toroid over here. And a lot of people did work on what's the best number of turns and size toroids based on how much power you're trying to run and what frequency bands you're trying to cover. Typically, these are made with high permeability material, like 43 material. And these want a 50 ohm transmission line since the input is 50 ohms and the output is 50 ohms. You want the impedance to match. The good thing about this is it has twice as much choking impedance as that of a 4-to-1 dual core guanella. So you might as well use a hybrid balun because you get more choking impedance for the same number of toroids. Okay, the next chart shows a picture of a hybrid balun. This was built by N4CY, who's on the groups.io OCFD group. He stacked one on top of the other and mounted them in a PVC case with a PVC cap on each end. And this used FT140 sized toroids. The Ruthroff used 14 turns, and the Guanala also was FT140 size. That used 17 turns of a small coax. This gave very good performance for him in a hybrid balun, and I estimated how much power this could take. I should have put it on the slide, but it could take 133 watts continuous for digital modes. You can't do that with a typical like a ARRL NFET half-wave kit. The toroid will not take that amount of power. This hybrid balun can take 133 watts continuous, about 333 watts CW, and maybe 550 watts on sideband. So it can handle a pretty decent amount of power for the pretty small size and low cost toroids. And this one, just so you know, this was done by Mr. Everett, N4CY. He called it the mother of all baluns. Everett Sharp did. This could take up to 1,500 watts in digital modes. And it's the Ruthroff was two toroids, two stacked FT 240 Type 61, and then the Guanella was two FT 240s. But note what he did over here. And this is very interesting. If you ever have to make a choke balun, instead of just taking a toroid and winding it with coax, or put two toroids together and wind this whole stack of two, take each toroid and wind it by itself and cascade them. Okay, what happens when you do that is the common mode current goes down by a factor of 2 of what one of these would take, because this has some common mode impedance, whatever that may be. At its peak, it may be 6,000 ohms or 8,000 ohms. So by using two of these, now the impedance is 16,000 ohms. So the common mode current will go down by half. But if you look at I squared R or V squared over R and these things, each one of these is only handling a quarter of the common mode power. So these will heat up a lot less than if you just stack two of them. So it'll take a little more coax, but they'll run a lot cooler. So if you try to make a 1500 watt NFET half wave transformer, you got a big problem there. Even the biggest ones that people use there, I think you have to put a small fan in to keep it cool enough. And I don't even think anybody successfully did that at 1500 watts with an NFET half wave transformer operating continuously. Yeah, you could do it with duty cycle, but not continuously. This will do it continuously, 1500 watts. How about that? Comment on these hybrid baluns. A lot of vendors don't make them properly. Um, if you can, you're better off building your own. You know that you have a good balun with no false promises. You'll reduce your costs a little bit. You'll be proud of what you built. So it's good if you can build your own. You can buy them, but it's good to build your own. I built several of my own. And here's a couple of notes on the Balun Designs 4116. Balun Designs makes good quality stuff, high quality materials, very good hardware, etc. And he sells a high power hybrid balun. It's rated up to 54 megahertz, 3 kilowatts. That means, I guess, with duty cycle. The problem with it is, I think he did it as a, forget if it was a hybrid balun or a 4-to-1 1L balance, but it didn't have adequate common mode on 80 meters. It'll work fine for 40 meters and above. It falls short on 80 meters. And I did some simulations myself on it, and yes, indeed, it doesn't work that well on 80 meters. Um, Rick Westerman recommended to a few people that you could remove the choke and rewind it with as many turns as coax that'll fit, then it'll work on 80 meters. Some recommended antennas, the 807 XX sold by Spider Beam. Um, it's about $250 for the heavy duty one. There's a 40-meter lightweight one, which was about $129. It covers 8 bands, 80, 40, 30, 20, 17, 15, 12, 10, and 6. 30 meters sort of, but you need a lower power and antenna tuner. 40-meter version will cover 40, 20, 17, 15, 12, and 10, and 6. And I listed links for reviews of those. Palomar Engineers also sells off center fed dipoles and even an end connected one. And their prices are sort of comparable. I have not had experience with theirs, but they're supposed to be good. There's a review on eHam if you want to look at that. I have had more experience with the 807 type antennas. And again, you could build your own. It'll work fine. With regard to end-fed halfway versus off-center fed dipole, I touched on this a little bit. The most important thing to know about these is that, again, the off-center fed dipoles have much smaller and cheaper transformers for the same amount of power. It's very easy to make a high power one, an OCFD, but almost impossible to make one with real high power full duty cycle for end-fed half-wave and transformers. Now you're going to say, but the end-fed half-wave, you could feed it from the end instead of feeding it from the center. Feeding it from the end is great because you have all kinds of possibilities for slopers, inverted V's, et cetera, and you can't do that with an OCFD. It's stuck with the damn coax hanging down from the middle someplace. How inconvenient. Well, I have news for you. This is changing. There's a fairly less unknown variant of the off-center fed dipole, which is an end-connected off-center fed dipole, abbreviated ECOCFD. It was invented around 2010. There was something that was introduced, which was a multi-band end-connected OCFD around 2010, but that is not available anymore. There were a couple of other guys that made some antennas, MORZF for 40 meters, and David Cutter, G3UNA, for an 80-meter antenna or a 40-meter antenna variant. Plus, there was a lot of work done by Mel Farah, K6KBE. If you join the OCFD group on groups.io, Mel Farah has a whole PDF file on making a very, very low cost and connected OCFD. Really high power, very low cost. That's worth looking at if you want to build your own high power OCFD. Now, how does it work? Well, a lot of VHF, UHF antennas are really vertical dipoles, and they have a sleeve on them. The feed line, one side goes to a quarter wave radiator. The outside of the coax is connected to a sleeve, which is a quarter wave long. So it's a vertical dipole. Now that was modified in an article by Phil Salas, 85X, who you might have heard about in QST magazine, May 2022. he came up with what he called an end-fed, center-fed 20-meter portable antenna, where he used the coax itself, the outside of the coax, as a sleeve, so that you don't need a separate sleeve. Now, the trick there was he had some kind of high impedance choking device at the end of it, at the end of the quarter wave, which isolated that section of coax from the rest of the coax. His wasn't a guanella choke, it was a interesting resonant choke. He made a choke and he put a capacitor across it to make it into a parallel resonant circuit using a low permeability ferrite. And that worked great, but it was monoband. That wouldn't work for multiband. So here's how you make an N-connected off-center fed dipole. Uh, this came from Mel Farah, K6KBE. You basically have a coax feed. Then you have a choke balun, which is a 1-to-1 monelic choke. Then you have a section of radiating coax right over here. This is sort of the short side of an OCFD. On the other side, you have the long section of an OCFD. So you have a 4-to-1 Ruthroff balun, and you have a 1-to-1 choke balun, but now these are separated. They're not all together in one little package. They're separated to allow for a radiating section of coax. And that's how it works. There's nothing to it. Well, there's a couple of little things to it. A couple of little things are this coax can become expensive. You want this to be lightweight, so you may want a relatively high power, thin coax. So the cost per foot is somewhat expensive. The other thing is you don't want to have to adjust the coax to tune the antenna. You want to make this length as accurate as possible so it's right the first time, and then you do some minor adjustment on the wire at the end. But again, this can use very efficient baluns, and it's end-fed. So it has the best of the end-fed half-wave antenna, where you're feeding it from one end, and the off-center fed dipole, where you have efficient transformers. It's just wonderful. Okay, this next slide shows a recent antenna made by DJ0IP. It's a relatively low power but very lightweight 40-meter end-connected off-center fed dipole. And this has all the dimensions and where you put the antenna and what kind of coax to use and so on and so forth. And this could be set up as an inverted V with a single pole in the middle and an inverted V fed at one end through the choke balun. It works great on the standard bands, but not on the walk band. 17 and 12 are usable with an antenna tuner, but it works great on 80, 40, 20, and 10. Oh, I'm sorry, 80, 40, 20, 15, and 10. I'm sorry, again, 40 meter, 40 meter one, 40, 20, 15, and 10. Sorry about that. But it's a great antenna, and it uses very, very efficient transformers. This is a 2 cascaded binocular cores, and I gave the part number there. And it's only 2 turns to make the Ruthroff balun, but you have enough inductance in there. I built one of these, and I built another one out of some other material, some 61 material. This one is 43, and a lot of these were built. I think more than 15 of these antennas were built with this type of Ruthroff. Just got to watch it with the 2 turns that the tubes aren't too thick. The wire's got to be reasonably thin because it's a tight 2 turns to get on there. The other choke balun was an FT140 43. And this was greater than 97% efficient. I simulated this, it's great. Here's the VSWR curve. It goes all the way up to 50 megahertz easily with very low VSWR. So this is a wonderful antenna. Um, and I'm in the process of building these. I built all the transformers. I got all the wire. I just got to put it together myself. This will take 130 watts continuous digital modes, 300 watt CW, and 650 watt sideband, and these little tiny transformers. These last slides show something that Rick Westerman and I have been tossing around. One day he shows up in one of the groups with a little hand sketched thing that was done by Tom Roush, WHJI, on a compact OCFD. And normally for 80 meters, a dipole, you need like 133 to 135 feet. This antenna only takes up 85.5 feet of width. It's like a C shape. You have a hybrid balun feeding the short end of the OCFD, and the long end is an inverted L. So you could almost think of this antenna as an inverted L with a single counterpoise, but it's really an OCFD. And you have the usual capacitor in the middle to move the resonance on 80 meters to where you want it with a bleeder. Now this antenna, I've simulated it. It's very efficient, doesn't need any coils at all. It has good antenna patterns, and it looks great on paper. We haven't built it yet. Neither one of us have got around to building it, but it's a really good, efficient, uh, compact 80 through 10 meter antenna. You can do the same thing on 40 through 10 with a 40 meter shortened antenna. It's less than 30 feet across. And again, it's a C shape. And I simulated this one also, and it has good performance. So if anybody wants to build that, let me know if it works. But of course, nothing beats a good beam. So yeah, but wire antennas can be good. Just to give an example, I could have put up off-center fed dipoles or end-fed half waves in my backyard. I started out with end-fed half waves, and I didn't bother changing it. But I'm a CW op and a 100-watt rig. In that class, I usually end up in the top 20% of all the operators, and I'm not particularly high up. So they do get out. And I'll say that the OCFD and the end-fed half wave, the radiation patterns are very similar. If you plot antenna patterns as a function of feed point, and that was done by somebody on QRZ. I think that was done by Dan McGuire, AC6LA. He made a dynamic picture of what happens to the antenna patterns with feed line. Excuse me. Sure, the antenna patterns will change with band, but they don't change very much at all with antenna feed point. So an end-fed half-wave antenna and an off-center fed dipole have very, very similar antenna patterns. How about that? Lastly, I put here some resource links. The first one is a very good, very in-depth presentation on OCFD antennas. It's like 2 hours long by Rick Westerman. It's in two parts. One is the theory for about an hour, and the other is how do you build them. That's a really good presentation. He put lots and lots of work into that. He also talked about the end effect in more depth. There's a Balun reference from Steve Hunt that I used for getting some of my information. And then has various baluns and antenna type things, component sources, which are very important, et cetera, et cetera. And if you want to see some of my other presentations, just write me they're on gnarc.org, gnarc.org, under presentations. And I have some on uh, triangular elevated, triangles, elevated square antennas, dipoles and doublets, end-fed half waves, and they're all pretty comprehensive. So if you want to look at those, if you have any questions, you can write me. I'll be happy to try to answer your questions. So let me know if you have any questions right now. I see there's 3 chat things in here. Next
Right
to
now,
the
we want the
89.
opinion of a Buckmaster.
Yeah, the Buckmaster is a very good antenna. Its only limitation is it's not designed for 15 meters. It has very low SWRs on all of the bands that they say they do. There's somebody in our local Stanford club who's a big pusher of the Buckmaster antenna. Again, its only limitation is that it does not cover 15 meters. It uses essentially something close to a 3-to-1 split, I understand. But it's quality, it's ruggedly made, it's good quality components. So you won't go wrong with it. Uh, it is not cheap. It's sort of at the high end of the cost for a commercial antenna. And in my opinion, why buy an antenna at that price that doesn't cover 15 meters when you could buy one from other vendors that do cover 15 meters with a different split and with probably more efficient antennas with the 4-to-1. The Buckmaster has a 6-to-1 transformer. Most of the other antennas nowadays use a 4-to-1 Ruthroff. So if there's any other questions, let me try to answer them for you. No, well, thank you all for listening to the presentation. And again, if you come up with any questions, feel free to write me at k1rf@aorl.net. Thanks for your patience, all. So I'm going
Thank you.
to
Thank you, Steve. I don't see any hands up. Barry's been handling the questions in chat. Anybody got any hands up to ask any questions? Great presentation.
I appreciate it. Thank you. I try to get as much important information as I could in as few slides as possible. And there's a lot of misinformation out there on all of the wire antennas. So I try to get everything all in one spot to at least get you a pretty good idea of what you're looking at.
Yeah, I recall that you sent me your copy of your slides. So we'll get that out there with the video so people will have all those notes and links and such as well.
Yeah, I think the presentations, the slides go away after a while, but I try to leave the links visible in the YouTube video so that you can get to the links from the YouTube video, or at least most of them.
Okay. Barry, how we doing?
We're good.
Okay. Well, I appreciate everybody. I think Steve, you did a great job. Not a lot of questions, but I'm sure there's we'll see them pop up when we get the YouTube out there. So anyway, thank you again.
Okay, thank you. My pleasure.
We'll pull the plug here, say 73s, and see everybody tomorrow night.